Hello, quick explanatory video on discrete random variables. We use these to model events of discrete events, and they're typically created from experimental results or just predictions of behavior. And you should think of them as effectively alternates to our regular distributions like binomial and Poisson. An example. We're interested in car occupancy during rush hour to see if car sharing would be beneficial. So we survey cars travelling from Brighton to London each morning, and we count the number of occupants in each car. Okay, and during that hour we count 400 cars rather with one occupant, 300 cars with two occupants, 200 cars with three, and 100 cars with four. So this over here, this bit here, our x is our discrete random variable. Yeah, random variable. Why do we, it's clearly discrete. It only has those values 1, 2, 3 and 4, and it's our variable, and it's random because in order to work out our probabilities here, we're going to assume we're going to use a relative frequency approach, and we're randomly selecting cars, the next one coming by, aren't we? So given that, here we go, that's that for you just to have a quick look at. There's our discrete random variable 1, 2, 3, and we've got probability for each, and using relative frequency approach, here it is. So total number of cars is 1,000, so the probability of having one occupant is 0.4. yeah, probability of two occupants 0.3, probability of three occupants 0.2, four occupants is 0.1. so that's pretty straightforward, something we would have done at GCSE. And as with any of these distributions, probability distributions, we can work out the central tendency statistics, mean, mode and median. Yeah, so our mode's 400, our mean 500th will be in there, won't it? So our mean is, our mode is 1, our median is 2, and if we want to find our mean, well, what do? We just start multiplying our probabilities out, don't we? So there's a 0.4 chance we've got one person in there in the car, 0.3 of 2, 0.2 of 3, and 0.1 of 4 occupants to the car. So the mean of that's going to be 2.0. And we can follow exactly the same approach, can't we, to find our measures of spread, variance and standard deviation. So we always start with our variance, don't we? So here we have our first part. Yeah, that's our sum of x squareds, isn't it? Rather than using frequency, we've multiplied by our probability. Yeah, so we've got 0.4 times the 1, and that's going to be squared to get our deviation. 0.3 probability of 2 squared, 0.2 probability of 3 squared, and 0.1 of 4 squared. So that's that part. And what do we have to do? Well, we have to take off our x bar squared times n. Of course, here, because we're using a probability n equals 1, doesn't it? So that's just our x bar squared, which we calculated as 2 up there, didn't we? There we go. So we end up with the first element there, all comes together, it gives us 5, our sum. Yeah. Then we have to correct for our mean of 4, by side of 2, and we square it to get 4, take one away from the other, and we know we've got our variance of 1 occupants. But that's in squares, of course, so to get to our standard deviation, we have to square root what we just did above, and in this case, we end up back at 1, don't we, to get to occupants. So all of that works. In fact, it's simpler than our other frequency calculations because we're working on the basis that n equals 1. Now, some of you who've done MEI particularly will be shouting, why aren't we dividing by n minus 1? Well, this isn't, ultimately we're not assuming this is a sample. We're saying we're using these probabilities as the full population. Yeah, so we therefore don't have to worry about adjusting recognize the fact that we've already used our mean to find our standard deviation. We're just so we don't have to worry about best estimate, so we're just going to divide by n. Okay, very quick. Next part, you'll also see, if you haven't done it before, seen them before, we use different terms rather than mean. We use expected values or expectations. Well, the expected value of x is actually the mean. Same formula here. We write it as E with x in brackets, and because we're not doing a sample, we would be assuming this is our population mean, for which we use the term mu, symbol mu. We also got our expected value of our variance, which of course is our sum of x squared times p, that's that term there, take away our mean, that would be, wouldn't it, in our traditional, that would be our x bar squared term here, is our second term. So it's exactly the same, isn't it? That's our equivalent to this, but rather than using n minus 1, we're using n, and everything's happy in the world, we're doing exactly the same calculations. So in practice, it's best thinking of all of these expectations as being weighted averages, yeah, where the weighting is the probability for each of the values of the discrete random variable 1, 2, 3, and 4. Finally, functions. We can actually play around with discrete random variables and the functions arising from them. So let's use this here. We'll extend our car survey model, and let's say it costs £10 a day to drive the car to London, and if there's more than one occupant, they're going to split it equally amongst the occupants. So if there's, here we go, if there's one occupant, he's going to pay the full £10. The two occupants are going to be £5 each, three occupants £3.33 each, and four occupants £2.50. Well, if we want to find the expected payment that we're each going to make, yeah, we're going to call that effectively the function of x, because it varies with the number of occupants, doesn't it? All we're going to do is think about the fact that there's a 0.4 chance we're going to pay £10, 0.3 chance of £5, 0.2 chance of £3.33, and a 0.1 chance of £2.50, which comes to £6.42. So therefore the average each occupant pays is £6.42 per trip. Pretty straightforward. You can do that for any function of the random variable. Okay, quick summary at the end then. Discrete random variables, they take discrete values, in this case 1, 2, 3, and 4. They occur on a random basis, you know, what's coming next. If we look at the next car, how many occupants are there going to be? But each value of the discrete random variable has a specific probability. So probability of having one occupant in our case was 0.4, probability of two occupants is 0.3, etc. We can carry out all the standard mean and variance calculations, but people will use the term expectation, and they'll rewrite the formulae in these forms. And if you have a function, some function of x, and you want to find the expected value of that, well, we just sub it in the same general expression, but here we, rather than using x there, we're going to use our g value of x, and then we're weighting it by p. So once again, it's a weighted average. Hope that's of use. Bye.